Now we've talked about HOPS methods for 4 days or 3 days. This is the 4th day. So you have some idea of what's going to be done by me today, I'd imagine. And the new wrinkle is that instead of computing water waves today, like we've ostensibly been computing the previous 3 days, we're now going to compute the spectrum of these waves. So I want to know if a water wave is linearly stable. Even more restrictive than that, I want to know if it's spectrally stable. So I want to compute the spectral data. So you might think about computing the eigenvalues of these waves, but strictly speaking, not eigenvalues. Right, so that's what I just said. Here's my outline. I'm going to talk about how one might use a boundary perturbation method to compute the spectrum. We're going to have plenty of time to see the strengths and weaknesses of such an approach. So if you think of a weakness along the way and say, why are you doing it this way? Probably I'm going to address that later in the talk, but feel free to interrupt me and say, this is a terrible idea because of this. And then hopefully I'll address it and you'll be like, oh, good, he thought of it. No, it'll be very satisfying for me if we have those questions. So after talking about how computing the spectrum, well, a nice aspect of these approaches is then you can naturally study whether the thing you're computing is analytic because you're doing an expansion in a small parameter and computing a series, and if that series is summable, then you've shown that you have analyticity in that parameter. So that's a thing we'll be able to study with these methods. To understand really what's going on, you really have to think about the spectrum or the waves in the context of resonant interaction theory. And I mean that in the context of the way that maybe Phillips or Harvey would mean resonant interaction theory. I got a review paper once that said, you don't have a forced linear oscillator here. This isn't a resonance. And they only knew about, the reviewer was only thinking about ODEs being resonant instead of the thing that we usually think about, I think, when you say resonant interaction theory. So that's what I mean. And I'll discuss that explicitly on a later slide. And then we're going to compute what I would call modulational instabilities by another expansion in the course of the talk. So the things we learned hopefully on Tuesday or Wednesday or Thursday now is how this TFE or boundary perturbation approach for water waves might work. So we take the things we want to know from the water waves, the speed, the free surface, and the potential, and we expand them as a series in the wave slope. Then we have to plug that into some formulation of the water wave equations, and it turns out the one that is numerically stable is the transformed field version of the water wave equations. So that means we map the domain to a strip after having inserted a kind of a transparent boundary on the bottom so that although the mapping is not conformal, so we get a non-homogeneous right-hand side, we only have to solve it in a strip instead of the whole original domain, and the width of the strip was one of the parameters that we got to choose. So you don't have to, although you might have to discretize this Laplacian to solve it instead of solving it explicitly, like you could if it was homogeneous, you only have to discretize a small strip. So this is all kind of a review, hopefully, from my lecture on Wednesday. So this is a thing we're presuming at this stage we can already solve. And we discussed what goes into solving it. You have to invert the linear stuff on the left-hand side that applies to each correction. And in order to make this right-hand side, or this left-hand side is not actually, left-hand side is not actually invertible because there are linear solutions to the water wave problem, but you can make the right-hand side in the range of this linear operator by enforcing orthogonality conditions, which effectively determine the speed here. And for the Stokes wave case, there's really only one solution you have to impose orthogonality to, and so there's only one unknown you need to set with these orthogonality conditions, and that's the speed highlighted here in red. If we were to do Wilton ripples, then there might be two orthogonality conditions, and I'd have to have another unknown here, and we discussed on Wednesday how you might make that series work. So now if you want to do the spectral stability problem, well, it's a very similar problem in character. Well, what do? You say I have phi bar and eta bar, the solutions from the previous slide, as a series in epsilon here. And what I want to do is I want to compute what is the equations for small perturbations to those solutions, which for the velocity potential I'll call u, and for the free surface I'll call zeta of some small size delta, in principle unrelated to epsilon. And you substitute that in, neglect quadratic powers of delta, and then you'll get a new linear equation, or almost linear. You get an eigenvalue problem, really. There are nonlinear aspects of eigenvalue problems. The eigenvalue here, lambda, is going to multiply the eigenfunction, so it is not completely a linear problem. So when we do boundary perturbation, we'll transform it to a sequence of linear problems, just like we did for the water wave. But so we did start with a nonlinear problem, and we will get to a sequence of linear problems, and they look almost the same. So if you weren't paying really close attention to the last slide, and you just blink and pretend u was your velocity potential and zeta was your free surface, then this is the exact same equations, except where you used to have a c dx, you now have a lambda. So the exact same procedure works to construct the spectrum at every order. You have to do all the same work you had to do, which means you have to invert this operator on the right-hand side, which you have to compute, and you have to impose orthogonality, which gives you lambda. But just like Stokes waves, the equations for lambda are all linear, so long as the kernel of the null space of linear, or the kernel of the linear operator on the left is one-dimensional. So in the context of spectral stability, a one-dimensional kernel means you have a simple eigenvalue, whereas in the context of traveling waves, a one-dimensional kernel means you have a Stokes wave. So that means it's very straightforward to compute the spectrum as a perturbation series around any simple eigenvalue. And this is what Dave had done before I joined him during my postdoc. He had constructed the series as a boundary perturbation series around any simple eigenvalue, and that's almost all the eigenvalues. Yes, Bernard?
So you're starting from lambda zeros that correspond to flat water?
Yes, exactly. So epsilon is the same epsilon in both cases. So it's the amplitude of the wave. So if the epsilon is 0, that's the flat free surface, and it's also the spectrum of the flat free surface. Right. So so Dave had done this already and computed all this spectrum, but he didn't find any instabilities. And that's natural, because instabilities bifurcate from eigenvalue collisions, not from simple eigenvalues. So if you only find the spectrum around simple eigenvalues, you don't find anything that you might want to find if you're interested in instability. And so then the next natural thought was, all we have to do is extend this in the same way you might extend Stokes waves to Wilton ripples, and extend simple eigenvalues to eigenvalue collisions. Yeah, Bernard?
Just like to provide a comment for, I mean, you know this, but there's people probably here who haven't thought about this problem. But the reason that what you say is true is because of the Hamiltonian nature. So a simple eigenvalue on the imaginary axis can't leave the imaginary axis, because there needs to be something that goes in the other direction, and so therefore you need collisions.
Sure. You could actually you could prove a very similar thing with this approach, even if it wasn't Hamiltonian, simply by inspecting the terms. So we actually compute
but the terms are
lambda.
what they are because of the Hamiltonian structure, because it's a reversible system.
I mean, you could do this in a non-time reversible system. As long as everything had the appropriate signs, you'd still get imaginary structure.
If you had a dissipative system, it's easy for an eigenvalue to cross the origin from negative to positive.
Yeah, I mean, not every non-Hamiltonian system, but some, sure. Okay, so there are a bunch of things that do change from the traveling wave problem to the spectral stability problem. The first of them would be the boundary conditions that you want to consider. So if you're considering traveling waves, you might non-dimensionalize so everything is periodic with period 2 pi. You can do that without loss of generality. For the perturbations, though, you don't want to restrict all your perturbations to be periodic with period 2 pi, because you miss a ton of perturbations. So in the context of this meeting, we call those subharmonic perturbations are lost if we restrict only period 2 pi waves. And so what's the appropriate boundary condition is the flow k or block boundary condition, where instead of the wave repeating after every 2 pi, you get an extra factor of e to 2 pi I p, where p is a real number, usually restricted between 0 and 1, or you can go minus 0.5 to 0.5, or you can allow all values of p, which is what McKay and Sapman would have done, but then maybe you do a little work that you didn't have to do. Right, so somehow the dependence on p here is going to be crucial in the next couple of slides, and I guess this is what I just said in the previous slides, that simple eigenvalues are like Stokes waves, eigenvalue collisions are like Wilton ripples, and the block parameter, well, that's actually like the bond number in the traveling wave problem. So there are going to be some block parameters where you have eigenvalue collisions, just like there are some bond numbers where you have Wilton ripples, but not every block parameter and not every bond number. So there are going to be some block parameters that are special in this context. So then you can turn the crank. And I'm not going to, I guess I am going to tell you the crucial parts of turning the crank, but one can do this and calculate all the lambda n's. Well, you could in principle calculate all the lambda n's exactly if you're willing to write solutions of non-homogeneous coefficient forced ODEs, which they're only forced by functions that you know. So you could do this in infinite arithmetic. We do it with the ODE solver that's very accurate. So you get essentially the same answer. So we calculate the first couple ones exactly, because those tell you the form of the series. So if you think about this, I compute exactly the first non-trivial asymptotic of the spectrum by hand, and then I figure out, oh, this is what the rest of the series will look like, and I have the computer turn the crank for all the later orders. So that's what I've said here, and you ultimately get the spectrum to, or the eigenvalue to whatever order correction you want, so I didn't put bounds here because it goes from 0 to whatever I choose. And if you wanted to compare the results that you get from using such a method to maybe a more classic Newton's method or eigenvalue solver where I fix an amplitude, calculate the spectrum, fix another amplitude, calculate the spectrum over and over again, these are the types of pictures you would get. So you would have like what I might call a direct numerical simulations would be kind of the things that Bernard or Olga would have talked about yesterday, or Katie, where Newton's method find the solution at every dot, or I could do this TFE style approach and find these continuous curves. Because the TFE solution gives me the lambdas, and then I'm free to plug in whatever epsilon I want. So at the cost of one computation of the lambdas, I find the whole curve. And now you can look even at the curve on the left and say, well, this must give me some extra cost that I've incurred with this method. It seems great. I find all the lambdas in one computation, and then I can vary epsilon continuously instead of having the cost scale like the number of samples I choose. But of course, there is a new cost that you can see is that, well, I depend on some analyticity of the spectrum, which there may or may not be. Or at least it may or may not continue to be analytic. So that's these vertical asymptotes here are a sign that something happened in the spectrum that stopped it from being analytic. And you can even look at these lines and guess what it was. Right? A finite amplitude eigenvalue collision will cause the spectrum to stop being analytic. So we can only find the spectrum up until, well, maybe there's a finite amplitude instability. Right, but we can expand around simple eigenvalues and about repeated eigenvalues and find the spectrum in either case.
What's the difference between the left picture and the right picture?
Well, so these I guess are two different block parameters or Floquet parameters. And it's just, so the spectrum in all cases starts out completely on the imaginary axis. And then we expand an epsilon and see where the trajectory is. So both pictures are stable waves. But this one, there's two simple eigenvalues on the imaginary axis, and this one I expanded around one repeated eigenvalue on the imaginary axis.
Which doesn't quite fit the theory that you had on the previous slide, right? So you have to do some extra work for that.
So this is the Floquet parameter where you had a repeated eigenvalue.
Right.
So I have done the work, is I guess.
Right, but then you start with a two-dimensional kernel.
That's right. So I'll actually discuss what is actually involved in constructing the series here. So this is what, I guess you could say that this would be exclusively computed with Dave's method, and then when Dave and I got together, then we updated it to do this in the same fashion you would for Wilton Ripple.
Up to the 0.15 or so on the left.
Yeah, exactly. It's still, as of right now in our discussion, you can't get that collision. That's right. So now you have these series, and you might ask things like, well, to what value of epsilon can I use such a series? For how large an epsilon is the spectrum analytic? And you can do things to try and estimate how large is the spectrum analytic. If you have the first order asymptotics, you can see what those would predict would be the eigenvalue collisions of opposite Krein signature and get a plot of how big of an epsilon you should be able to use your method. Or you can say, well, why only use the first order asymptotics? Because I have all the orders. So I could take all these coefficients I found, and they're effectively a Taylor series of my function, and see to what extent is that summable by like doing the ratio test or the root test or whatever test you like to see if series are summable, and get an estimate for the largest epsilon at which the spectrum is analytic. Or you could do Pade series or Pade interpolant and find the first pole of that Pade interpolant and say that's the extent to which my series is summable. And all of them give you very similar answers. Maybe they give you different orders of magnitude, or not orders of magnitude, different values for the epsilon, but the picture is qualitatively the same. So you've got a bunch of different approximations for how far it's analytic, but qualitatively, what you see is I have large epsilon where the spectrum is analytic. So this is here, bond number and Floquet parameter for a one-dimensional free surface. So I'm changing how much surface tension there is. You might have large radius of convergence, or you might have small radius of convergence. So on this plot, we can actually see some things that we might recognize as places where the series wouldn't be analytic in epsilon for reasons that we recognize. So for example, here's Benjamin Fear. This is in deep water. In deep water, Benjamin Fear, the instability is for bond number bigger than 1/2, and also less than some irrational number that has to do with the minimum of the group velocity. So it's not every wave in deep water is Benjamin Fear unstable. Long waves are. It's effectively a small value of sigma. And really, oscillatory capillary waves are, but there's a range where it's Benjamin Fehr stable, in between the minima of the group velocity and the phase speed. In between the minimum of the group velocity and the Wilton ripple.
Okay.
Yes.
I'm confused. I thought the picture was about the disk of analyticity, but you're drawing conclusions of instability.
Yeah, so the disk of analyticity is limited by eigenvalue collisions, right? So if I know there's going to be an eigenvalue collision, like Benjamin Fehr is an eigenvalue collision that actually happens at finite amplitude away from p equals 0. So if I'm not at p equals 0, it happens at finite amplitude, so that's what I'm seeing here.
But it should happen close to p equals.
Yeah, at p equals 0, I don't get anything. So the black line traces the axis. But as I move away from p equals 0, I also have small radius of convergence. Because the Benjamin Fehr instability is still present, it's just a little bit farther away in block parameter space. So if the instability is continuous, as I move closer to the axis, I'll get smaller radius of convergence.
But Benjamin Fehr is a collision at the origin.
I agree.
And Krein signatures don't allow you to draw a conclusion from collision at the origin.
So we'll see. I'm going to explain this explicitly in a couple of slides, and maybe that'll help. So the radius of convergence, that it gets limited by Benjamin Fehr, scales linearly with p. So that's what we'll see. And so that's the manifestation is here in the graph. But similarly, I mean, there's other things that other eigenvalue collisions that happen in this problem. So this dotted line is a triad, and in the neighborhood of this triad, we also have a spectrum that has very small radius of convergence. And then down here, well, there's all kinds of other things going on. And as soon as you see this triad that seems to limit the radius of convergence, you might say, well, does every eigenvalue collision have vanishingly small radius of convergence? If that were true, you would never find any instabilities with this method because you couldn't compute the spectrum around any eigenvalue collisions. Well, it turns out that at the center of this band of triads, so I'll draw one more slide. So this is the same graph as before, but now I've labeled all the wave resonances that happen, or at least the first 100 or so. So the pink curve is this triad, and it's in the center of some band of places where my spectrum seems to lose analyticity. The red curves are a ton of opposite Krein signature wave resonances. They might be quartets, quintets, etc. And the blue curves are a ton of the same Krein signature eigenvalue collisions where we wouldn't expect instability. And it seems like the blue curves have nothing to do with the radius of convergence of my method. The pink curve certainly does, and the red curves maybe do, but in a way I don't understand. So where these resonances are dense, these wave resonances are dense in the plane, probably this is not the appropriate method to use, even though it seems to work. But still I'm bothered because I did all this work to find the instabilities, and it seems like I can't use my method. But these black bands are where there wasn't actually a repeated eigenvalue at 0 amplitude. Only at the pink curve did the spectrum have a repeated eigenvalue. And if I were to take a slice of this picture, like say horizontal slice at some sigma, at sigma, at the bond number equals say 2 and change, what does the radius of analyticity look like? The radius of the disk of analyticity. Well, it does go to 0 as I get to the special block parameter where there's a triad, but if I actually expand it at that block parameter, what I get is quite a large radius of convergence of the method. So this is what, effectively, you can think of every block parameter on here as the spectrum is all simple eigenvalues, except this one right here, about 0.2, where there's a repeated eigenvalue in the flat configuration. And then you can do the expansion like I would have done with Wilton ripples, and then you can find the spectrum up to quite a large amplitude. So it's not that the spectrum really lost analyticity, it's that you're using two different expansions and you're not matching them properly. Right? So if I try and expand and say the spectrum is all simple eigenvalues really close to the resonance, well, effectively you have like a small divisors problem where you should have expanded in not just amplitude, but also in frequency. So that's what you have to look forward to in our next discussion. So I've said the words triad and quartet and quintet, etc. a lot of times in this talk. And when I say those, I mean them in the context of resonant interaction theory. And I think that's the way to categorize and understand all of these instabilities and collisions that I've talked about in the previous couple of slides. So what do I mean by resonant interaction theory? I mean, let's say I want to see the dynamics of eta and I know that eta is basically a sum of a couple frequencies. And so I have here a sum of a couple free wave solutions this is here all written for the free surface, so for the traveling wave. Sum of a couple frequencies, and they all have some amplitudes, and they're small, and I allow the amplitudes to be almost constant, but maybe varying on the slower time scale than I allow the free wave to move at. And if you plug this into the water wave equations, what happens? Well, most of the time, you can plug it in and turn the crank over and over again and compute all the corrections without doing anything really. Just, okay, I plug this in, this is leading order solution. I can find this guy by plugging into the right-hand side and inverting the linear part over and over again. And most of the time, the solvability conditions are trivial, but sometimes they're interesting. And they're interesting exactly when some of the frequencies here in space and in time resonate with one another. And when they do, then you have to add non-trivial time dependence to these ANs in order to have a solution to each order. So the simplest possible case is when 3 of these wave numbers, the Kn, sum to 0, and 3 of their temporal frequencies sum to 0, and you call that a triad. And if that's the case, well then I have to add time dependence at the smallest possible power of epsilon inside of the amplitudes, and you get an equation that looks like this that you might use to govern the dynamics of these amplitudes at first order. And in the context of these equations, you could determine whether or not waves at a certain frequency, so think of there's a bond number in here, so that's what I mean by frequency really. And what waves at a certain bond number, I could see if the Stokes waves were stable to triads by saying, all right, my Stokes wave is going to be A1, and I'm going to start with the solution to these equations where A1 is constant and A2 and A3 aren't there. That would correspond to a Stokes wave, which is supported only at one frequency. And then I could see in the context of these equations, is that solution stable? And I'll get non-trivial results. I'll find out the Stokes wave is stable to these triads or not, just by going this far. So if that's true, somehow my perturbation expansion should capture that same result. That if to this order I can determine whether Stokes waves are stable or not, then to that order in my spectral calculation I should be able to determine whether Stokes waves are stable or not, so long as I'm doing the expansion near where there's a triad. And if you want to read about this type of thing, there's a nice book by Craig called like Wave Interactions and Shear Flows or something like that.
Okay.
Yes?
So this is for near zero amplitude.
Small amplitude. So in fact, everything here is in small amplitude because I'm expanding as a series in amplitude. So there's only some.
Here. Well, the numerics before it wasn't. You could, wherever you
Well, I mean, I can vary amplitude, but at some point the spectrum is going to stop being analytic.
Right.
And that's not going to be at a huge amplitude because I am expanding around amplitude equals 0. So smallness is somehow encoded into what extent the spectrum is analytic. Right, so I said that this is connected, and so far the only way it's connected is I said they should give you the same results. But they are actually more connected than that. So what I'm doing here is I'm expanding around the free surface or the flat free surface traveling wave, and then I'm computing the corrections to that. And about the flat free surface, I can solve the eigenvalue problem exactly and write what the eigenvalues are. So I called them here lambda naught plus minus, that's standard convention. And what is lambda naught plus minus? It's plus or minus the dispersive part of your traveling wave. So here's the dispersion relation with an I, minus IC, and K is here the frequency of your perturbation, not of the traveling wave. And if I wanted to say I have an eigenvalue collision of the flat state, that means I have this guy, I'll write on the board now. I have lambda naught of K1 equal to lambda naught of K2. And they both have plus or minuses, but the calculation doesn't really depend on that. So if I have, so this is an eigenvalue collision. If that's true, well, it doesn't take very long at all to see, okay, I can put this on one side and this on the other side. And well, that means I can subtract the omegas over here and add the K1 over here. You get an equation that looks like this. C naught, that's the phase speed of the wave, which I've non-dimensionalized to have K equals 1. So typically you might write Cp as omega over K, but since K is 1, it's just omega. So that means I could have replaced this C naught with omega of 1. And if K1 and K2 have the same block parameter, which is what happens when I find a collision, then K1 equals some integer, maybe I call it m plus the block parameter, and K2 is another integer, maybe I call it n plus the block parameter, and when I take their difference, I get an integer, because they have the same block parameter, so their difference is m minus n. So really, this is an equation that says omega of K1 minus omega of K2 equals m copies of omega of 1, of the underlying wave, not of the perturbations. So really, this is a resonance condition exactly of this form. Only, how is it of this form? So typically, you'd call a resonant interaction if you had a sum of frequencies equals 0 and a sum of temporal frequencies equals 0. Well, for an eigenvalue collision, I have the difference between two waves is an integer. Well, an integer, I can even say an integer times k naught, because k naught is 1. So whatever integer it was, I'm really having a bunch of waves adding together, k1, k2, and then m copies of k naught. And similarly, I'm having the temporal frequencies add up. Omega 1 minus omega 2 is the same m copies of omega naught. So it's just a special case of resonant interactions, where if m is 1, then I have 3 frequencies here, and 3 frequencies here, so I have a triad. And m is 2, I have 4 frequencies, I have a quartet, etc., etc. Okay, so then what do you actually have to do if you have an eigenvalue collision and you want to compute the spectrum? Well, you have to do the same things as you had to do for Wilton ripples. So here we'll start with m equals 1. So here's my triad, k1 minus k2 equals k naught, omega of k1 minus omega of k2 equals omega of k naught, and you plug this in and you get the leading order solution, and you go to the next order, and that's the first time you have to compute a solvability condition, and the solvability condition looks like this. Almost exactly the solvability condition we presented on Wednesday. So you have to impose solvability at the first frequency in your null space, here it's k1, and the second frequency, there it's k2, and you get you'll always get the linear part, or the lambda 1 correction times the linear solution. So this is just lambda 1 times e to the ik1. You will sometimes get triad interaction. So that's what you get here. So tau 1 is the triad interaction coefficient between k1 and k naught. And here what we've done is we've said k1 minus k naught equals k2. So effectively, this is the triad interaction coefficient that you get when you say k1 interacts in the non-constant coefficient linear term of your perturbation expansion, which has contributions at k naught and then gives you k2. So that's how you get this guy. And then similarly, k2 interacting with k naught gives you k1. That's how you get this guy. So these are the interaction coefficients from your triad equations. And then you get a solvability condition for your unknowns, which are here beta naught, which I guess in today's lecture I didn't define beta naught, so I should define it again. Just like for Wilton ripples, where the leading order solution was e to the I k1x plus beta naught e to the I k2x. So is the leading order contribution to the spectrum for this is zeta, as well as I write zeta, which is not on the board, so you can't tell how poor my zeta is. So the leading order contribution to the perturbation to the free surface is also supported at 2 frequencies with an unknown coefficient, because the linear problem supports superposition. But the nonlinear problem does not, and what do we have to solve for this beta naught? I guess beta naught, so this k2 is not arbitrary k2. It's actually, what is it here, 2 minus 2 minus 1, I don't know. It's here, right? K2 is k1 minus k naught, so k1 minus 1. So 2. So this is not, the nonlinear problem doesn't allow arbitrary superposition. In fact, you have to solve a nonlinear equation to find beta naught and lambda 1. But that nonlinear equation is simple. In fact, if you were to do a little bit of algebra on this, you'd find it's a quadratic which is already factored for you. And so you can find lambda 1, and lambda 1 will have some form in terms of the nonlinear interaction coefficients, which are both imaginary but have a sign that you don't know. So, I mean, you've calculated it, but I can't tell you for every single wave it's unstable or stable. You can actually calculate it, which we've done, and find out if every single wave is stable, or you could use, say, Hasselmann's criterion and find out if your wave is going to be stable. And once you find lambda 1, all the remaining equations are linear, and you can turn the crank and find lambda 2, lambda 3, lambda 4, etc. And here's an example of what that might look like. If you have an instability, you find, well, I guess there's the solid curve as the results of our numerics, and the dots are the results of somebody else's. It almost is just lambda 1, right? But at least for the amplitudes that I'm computing, you learn almost everything about the spectrum just by the first order correction. So the asymptotics are almost as good as the numerics if I just keep the first order correction. And if I try and do the same thing for quartets, the story is again quite similar. I guess I don't want to go through all the exact details except to say that you still have effectively quartet interaction coefficients. So now K1 minus K2 is twice K naught, so I have to have K1, or here, yeah, K1 interacts with K naught and minus K naught to force K1. K2 interacts with K naught 2 times in order to force K1, et cetera, et cetera. The solvability conditions are different from the Wilton-Ripple case in that they're not cubic, because I didn't have a cubically nonlinear problem to start with. What I had was an eigenvalue problem, which was quadratically nonlinear. So I don't have the opportunity for my unknowns, which are effectively here beta naught, to multiply, say, another factor of beta naught like I could in the Wilton-Ripple case. The only thing it can multiply is lambda. That's the only other unknown. So the nonlinearity is just quadratic, and I can still solve the quadratic. The only new wrinkle is it's no longer factored for me. So the solution is kind of the general solution to a quadratic equation instead of this plus or minus solution. And what that means is that these PIs are imaginary, so I'll generally have an imaginary part to my spectrum, and then I can still get instability, but now I need instability when the discriminant underneath this radical is positive, I suppose. And here, since these guys are imaginary and they're squared, this is necessarily negative. This guy could have positive contribution, and so I could give you a necessary condition for instability that this product is positive. And regardless of such a necessary condition, we explicitly have computed all these things, so we can also just plug in the k's that you want. Yes, Harvey?
Does it matter to you whether the k's are positive or negative?
No. No. So
the minus sign could be a plus sign?
It could be a plus sign. So I mean, you can choose whatever signs you want in general in front of these things here and there, just so long as they add up to one another, so plus or minus. So you could think that I've hidden whether k is positive or negative in here. But I should choose a convention when I do the series just so I don't have to consider every possible case, because they're the same up to relabeling. So that being said, after having done this, you almost never find this condition that the product of P1, P2 is positive. So Dave and I published a couple papers before we found any quartet instabilities. This was pretty troubling because during this whole process, we were corresponding with Bernard and Katie and Olga, and they were finding quartet instabilities all the time. And so, well, one of us had to be wrong. It turns out neither of us was wrong, but our method couldn't find their instabilities. So that's disappointing. So why couldn't our method find their instabilities is because their instabilities move in the p epsilon plane. So if you vary amplitude, the flow k parameter where they find instability is not the same one for all epsilons. It typically is a different flow k parameter at each epsilon. Maybe a band of flow k parameters, but that band typically moves as a function of epsilon. So since we were expanding in the p epsilon plane just vertically, if their band moves, we can't find it. And that means that when their band moved, if I were to take another trajectory, so say I take a trajectory here, and there's an instability that started here, say on the red line, and moved to the left, what I would see is analytic spectrum, analytic spectrum, analytic spectrum, and then an eigenvalue collision at finite amplitude, which would look like a loss of analyticity. But really, it's just a loss of analyticity because I'm moving vertically. If I had been moving on an angle, say starting at the resonant flow k parameter and moving diagonally, then I wouldn't have any new eigenvalue collision. I would have a spectrum that was analytically connected to here that just moved to the left. And so that's what needs to be done to be able to compute all the same instabilities that Katie and Bernard's group computed. And you can do it. In fact, I've done at least the asymptotics, and someday we'll do the numerics. But even the asymptotics tell you some interesting things. So I don't want to really belabor it except to say that you expand the flow k parameter and you get things that you would expect to get. You get corrections to the eigenvalue that have to do with the new speed that you're effectively moving at. And you get, here is the same interaction coefficients that the triad had before, but now they're shifted by something that has to do with how far off your flow k parameter has changed. And I guess the important thing to notice is that, well, this is a real thing squared with a negative sign, so it's certainly negative. So the effect of modulating your triads is to make the instability smaller. Right? This is imaginary. This is the thing that might create instability that might be positive. And if I subtract something from it, I make it less positive, so I make the instability smaller. So where is the instability the biggest is if this thing I'm subtracting isn't there, which happens at p equals 0. So for triads, we in fact had already computed the biggest instability, because it lies when p1 is 0. p1 is the distance away from this resonant configuration. It lies in the middle. So when we found triads and said, oh, triad instabilities are there and big, well, if they're there at all, they're there in the middle. They're there at the case that we compute when p1 is 0. For quartets, however, that's not true. So if you do the same expansion and you just tried to vary the block parameter by epsilon p1, you find that everything has the same stability that it had before. But if you then say, okay, let's say it doesn't vary like epsilon p1, let's say it varies like epsilon squared p2, then you get a non-trivial correction, which still has an imaginary component, an imaginary shift of speed, the same stuff as before. So this is the guy that needs to be positive to have instability in the previous case. But now I have, so in fact, this guy still needs to be positive, but before it got to be canceled out sometimes by p22 minus p1 squared, which was negative, right? If you actually multiply this out, what you find is that you can have a new range of instability just when, well, the whole discriminant is positive. And when does that happen? That happens exactly, so you can find the roots of this guy here as a function of p. It's a quadratic inside. You find the roots, and you find that there are two critical values of p2 where the argument of this square root is negative, is positive, so that you get real parts of the spectrum, and it lies between two values of p2, which typically, well, which often have the same sign. So what that means is the instability doesn't typically include the middle. So if we use the old non-modulational method, you would move with p fixed in this plane, and you would find that, well, there's not an instability, and your spectrum seems to be analytic up to a large amplitude. But if you moved over, then you'd find, oh, now the spectrum's not analytic for very large amplitude, and there's some weird one-sidedness to the radius of analyticity that I predict. Well, that one-sidedness is because there is an instability just in a really small spot. This is actually two curves here. P1 and P2 are quite close together for this particular problem. So there's a really small band of instability that we predict with the asymptotics that you could then compute and see where is now the biggest instability. It's now between these two curves, so almost on a line in this problem. And now with that extra knowledge, we can compute such an instability, which you couldn't compute before. And you can also understand, well, is the spectrum actually not analytic? Well, it's not only analytic in this direction, but you could compute an analytic spectrum if you stayed within the band or stayed outside of the band. All right. And then you could say, well, now I want to do all the other cases of M when we already did 1 and 2 for triads and quartets, and you could do quintets, etc. And what happens there? So if there are no triads, even with modulation, the first order solvability conditions will generally say that the first order correction to the spectrum is true imaginary, and the contribution at the second wave number is 0, but not always. So it could happen that these two conditions are redundant, that lambda 1 equals I C naught CGK1 times P1, and lambda 1 equals I C naught CGK2 times P1. Those give you the same information if the group velocity at both frequencies is the same, which happens, say, for example, in Benjamin Fear, or any other time the two group velocities are the same. And since the group velocity only depends on the modulus of the wave number, so anytime the modulus of the wave numbers are the same, you'd also have that condition. So without triads, the first correction to the spectrum is 0 unless you have this degeneracy in the group velocity. And the same thing happens if I go to the next order. So let's say I choose P1 to be 0 and move to so that I don't specify an imaginary first correction to the spectrum. And then I go to the next order, hoping to still get some nonlinearity that still gives me a real correction or instability in the spectrum. Well, then I get another set of equations. It looks quite similar now. It has a term that's not dependent on the perturbation of the block parameter. But they're still almost the same equations. Now I would want something like I C naught CGK1 P2 minus this imaginary thing that has to do with interaction of K1 with K naught and K naught, so a quartet interaction coefficient that only depends on K1 and K0. I need somehow that to have a matching condition with the quartet interaction coefficient and the group velocity at K2 and K0 and K0. And generally that won't be the case, but sometimes it might be. In fact, I could think of this as an equation for P2. In fact, if you tried to say this whole guy is equal to this whole guy, lambda 2 cancels out, C naught cancels out, and you get an equation for P2 as a function of these difference in the nonlinear interaction coefficients, which means that there will be a P2 along which beta naught is still not determined, and you'll get some nonlinear equation for beta naught and lambda 3 or lambda 4 or whatever you want. So what does the scaling look like? If I have quartets, I'm going to get two different values of P2, so I'm going to get instabilities between two quadratics in this plane, or between two square roots, I suppose. If I have triads, I'm going to get instabilities between two lines if the leading order triad was unstable. And if I have anything higher, I'm going to get I'm going to get instabilities which are, at first approximation, on a curve which scales like P naught is, or P is, not written here. P is P naught plus epsilon squared P2 plus stuff that I didn't calculate. But if I want to know where it is, I know at first approximation where it is. And then the width around this thing that looks like square root might be like epsilon cubed if there's a quintet, might be like epsilon to the fourth if it's a sextet, et cetera, et cetera, et cetera. Yeah, Bernard?
Is that a cartoon or is it?
But this is a cartoon.
Okay.
Yeah. So that's the story, at least the story as far as I'm going to tell it, if we only consider one-dimensional perturbations. Well, almost the story. So I keep saying Benjamin Fear, and you should also compute the Benjamin Fear instability. What does the Benjamin Fear instability look like in this plane? Well, it's kind of a triad. It's also kind of a quartet. It's a degenerate triad. It's kind of a degenerate quartet, but it's also the collision of four eigenvalues, which almost never happens, but does happen once all the time for every single bond number or depth that you want, and that's what we call the Benjamin Fear instability. It has no instability if I stay at k equals 0. So it's a modulational instability between small flow k parameters left and right. So if I were to draw a picture that looked like this, it would have a band on one side of instability, a band on the other side of instability, and a band in the middle where there's no instability. So you must do modulation to see Benjamin Fear. That's why we call it a modulational instability. You can't see it if you just fix the frequency. So that can be seen if you just find the asymptotics of the spectrum and see, okay, lambda 1, well, it has a contribution of P1, but it's pure imaginary. So at order epsilon, you don't get Benjamin Fear. You get an imaginary correction to the flat state spectrum. So here's their four eigenvalues that collide the flat surface. But if you find lambda 2, well, it has an imaginary correction due to a speed shift, and then it has some radical that could or could not give you instability, depending on a sign of a quartet coefficient. So this would be like the coefficient of your cubic term in NLS and the linear dispersion relation. And their product tells you whether you have instability or not. Yes, Bernard?
This is prior to the separation of the figure 8.
Yes. So when the figure 8 crosses the origin, I agree. That's what. So here, there's no figure 8 because this is 1D. Here, there's just two intervals, but there's going to be an x in a second.
So the first line there is basically you're looking for the cross. That's
The center. Yeah, exactly.
Right. You're looking. I mean, this is Rowland's approach. But then, so there's two criteria. There's two different things now that limit your epsilon. Namely, one is the anisotropy of.
Yeah, and now how far I can move in P.
But then there's a second amplitude restriction, which is that ansatz only captures when you have the cross at the origin, which is once the figure 8 separates, you no longer have that.
Sure. So in general, there's going to be when you expand the spectrum, there's a new restriction on epsilon. Right? When you expanded the wave speed, there's a restriction on epsilon for how large your traveling wave converges. But now you also expand the perturbations, and there's a restriction as to how long those lambdas are also analytic. So lots of stuff has to be analytic to be able to use this approach. But you can capture the exact same instability criterion that you found before, and or that people would have found in NLS before. So you have instability at P1s here. So P1 is the thing that determines whether you're unstable. So the instability scales linearly with distance away from the block parameter P equals 0. But it occurs if P1 is 0, there is no instability. And if P1 is, makes this guy 0, there is no instability, and only in between. So it's two bands where the center point is stable, and the edge of the bands is stable, and in between somewhere you have instability. So that's why you couldn't compute Benjamin Fear with our previous approach, because if you set P1, the modulational component, to 0, you don't get instability. So although we only did this for collisions of 2 eigenvalues, and this is a collision of 4, extending our method to 4-dimensional null spaces in general wouldn't do you any good, because you still wouldn't be able to compute this. So really what you need to do is extend it modulationally, and then decide what degree of null space you want to consider. And you can do this, of course, all in 3D. All you have to do is let the block parameter be a vector, expand that vector, and then you get almost the exact same results you had before. You just have to think of the group velocities as now vectors, and the block parameters as now vectors. And triads have almost the same story. So there's a triad in the middle, and as I move left and right, the instability scales linearly away, but I can vary the transverse direction and it doesn't affect the size of the triad or of the instability. And quartets have, again, a similar picture. This is now the P2Q2 plane. So again, you don't get quartet instabilities if you try and scale the modulation with epsilon. You have to scale the modulation with epsilon squared. All the terms look the same. You just have to do the vectored version of the group velocity in the block parameter.
That's just a dot product?
Yes.
Or you can multiply?
Yeah, it's just a dot product. Katie?
Yeah, is this three-dimensional perturbations to or two-dimensional wave? Or
Yeah, so it's a planar Stokes
Okay.
wave still. That's right. I didn't update all my formulas for short-crested waves, but you could do this for short-crested waves, and it wouldn't be very different.
And you're looking at the amplitude of the real part here. I mean.
So
that's
this
the
is so yeah.
component.
So I should say that red is instability, the magnitude of the unstable part of the spectrum. Blue is pure imaginary spectrum, and this is the Q2 P2 plane. So you could think of this as a zoom in around the crucial block vector, right? Because I'm scaling both axes with epsilon squared, so the epsilon says I'm close to that crucial block parameter, but the corrections have the same scaling. So it's effectively zooming in and out, and how fast you zoom in and out scales like epsilon squared. So this is local to the crucial block parameter, which is the origin here. That would be when I'm still at K naught, no matter what epsilon is. And just like before, quartets typically don't include the crucial or the resonant block parameter, typically doesn't include the instabilities at later amplitudes. So just like before, where I shot that vertical line and I missed the instabilities, you would miss them in 3D most of the time as well. So the band of instabilities lies separate from the origin. Yes?
In 1D, you don't have to go from -1/2 to +1/2 for K parameter because of symmetry.
Mm-hmm.
You can just look at half of it.
Uh-huh.
What happened to the symmetry here? I mean, if I take a slice to just fix a Q2, I don't see a symmetric picture.
So this is not block parameter. This is local. This is the correction to the block parameter P2. So this is if I take one set region of that plane that you know is symmetric and I zoom in really close, it doesn't have to be symmetric around every possible point that I might expand around. It has to be symmetric as a global picture. So this is the local zoom in near a critical block parameter. Right, and it will not be symmetric. In fact, so you can also do Benjamin-Fehr in this setting, and Benjamin-Fehr happens to be centered at the origin, so then your pictures will be symmetric. But if I had centered any other non-zero block parameter, or not at the origin, then I wouldn't get symmetric pictures. But again, it just amounts to some, well, this is now a matrix, it's the Hessian, and I still have things that I have to vectorize and take dot products. This is now a matrix product. And then you get here's your X Bernard that you want to see, that modulational instabilities predict your X. Your X is now, that's for long waves or for zero surface tension. But if you include surface tension, Benjamin-Fehr doesn't look like an X. If you include, for example, if you look at sigma equals 1, then Benjamin-Fehr looks like a torus. There's no instability still in the middle, but there is instability in every direction. And that, roughly speaking, corresponds to a change in the sign of the terms in this Hessian. So you would have, say, the elliptic NLS has coefficients of the same sign on both linear terms. That's encoded in here and gives you a picture like this. This is what you need to compute gravity capillary lumps, and this is what you need to prevent gravity capillary lumps, and maybe have only planar solitary waves. So it looks like a perturbative approach with modulation should be able to compute Benjamin-Fehr even in 3D, no problem. And now, so I'm being a little lazy with you because I didn't turn the crank for m bigger than 2. So you should be able to say something about m bigger than 3, and that's what historically has been focused on. So unfortunately, McKay and Sappin's m is not my m. So from my perspective, this is a sextet and this is a quintet, so that would be my m equals 4, my m equals 3, more than I was willing to do. But they do observe that the instability doesn't, in block parameter space, so PQ, just like I've been talking about, doesn't include the resonant configurations when you move to finite amplitude. So here is 0 amplitude, the exact resonant curve you can get from linear theory, and here's where they say the instabilities are for finite amplitude, so it's shifted down. And same thing, here's 0 amplitude, and here's finite amplitude, shifted down for the waves that I didn't compute for you today, their local structure. But I almost computed them, because I told you where P2 would be. I told you where the center of those bands would be, and so now this is my computation of the exact same picture, and if I vary amplitude, well, the center of those bands that I can predict asymptotically moves down. And I don't have an overlay of the two figures, unfortunately for you, because it would be a lie, because they don't tell me what epsilon is. They tell me bigger than 0, and it's kind of a cartoon where the q-axis isn't even labeled. So I expect in the lecture notes I will put this picture labeled, because Katie has nicely volunteered to give me a more recent computation of the McKay-Safin picture with color and epsilon explicit. And so in the lecture notes, you can expect to see this type of thing, well, probably not as an animation, but overlaid with modern numerical results to show that these asymptotics work. That's all I have to say. So, yeah, I could comment on the references, but you can also read them. And I'll leave it up during questions. Yes, Bernard.
I'll hog the conversation. Harvey asked a question about K being negative. On that same slide, you also had omegas. One of the omegas has to be positive, and the other one has to be negative, right? So you need to take an omega from opposite branches of the dispersion relation.
Yeah, if I'm going to get the instabilities, you're right. They're opposite Krein signatures. That's true.
So yeah, so it should really be omega 1 and omega 2.
Yeah, you're right. I didn't label the plus minuses in my omegas, because this isn't actually what I do, right? I actually collide the eigenvalues of plus minus, and it happens to amount to something like this.
Right,
so you could track the signs in each of them. So that's where I suppose you could say that this is omega plus and this is omega minus. Right. Okay, so now we have coffee, maybe, but we at least have like a 3-hour break. So everyone enjoy that and try not to get too hot before the end of the day.
Can you do something so that you don't just have an isolated problem at that one point, or is that what you already explained? Like, can you bring that whole curve up so that it doesn't go to 0 anymore? Radius of convergence.
So you mean, I went too far. In this picture?
Yeah, somehow get rid
Yeah,
of that
so
problem.
what I would do effectively is I would like to expand here, get some new radius of convergence way out there, because now I know I can go this far in the middle, and I know I can vary with epsilon and not hit anything bad until I get all the way over here. So I think I have that picture somewhere. Yeah, all the way over here. And so that point that I said I can converge to is way up off the picture. Here's 0.2, that was a 0.35. So I expect to be able to compute all the way out there. And in fact, I really expect to be able to stick another point in here and modulationally expand there and only use 2 points and get, or maybe 3, and get this whole axis. So that's forthcoming. It hasn't been done, but I expect to be able to compute this whole guy with one expansion around there, maybe there to get that guy, one here to get that guy, and one here to get that
So you
guy.
haven't done it for the water wave problem, but it's standard Cato perturbation theory, right? So I mean, in this case, you know you're going to get. I mean, you're going to need a series with square roots instead of the Taylor series.
Well, it's not all square roots, right?
Well,
Triads are not.
Well, it could be higher.
It could be higher.
Fractional powers, but or lower.
Well, the leading order is going to be, you call square roots, I call epsilon squared. Right? It just depends on which way you expand. But the leading order about triads is just going to be linear. And then depending on which you have to choose the appropriate scaling. I agree. Okay, thank you very much.